All right, so this is section 11.10, video number 3. This will be our last video. We've got 4 examples to go. So we've been figuring out how to create Taylor and Maclaurin polynomials of functions that are not polynomial. In the last video, we created a bunch of them by manipulating known Taylor polynomials or Maclaurin polynomials. And in very specifically the last example, we were able to multiply x times cosine of x, create the Taylor polynomial for cosine of x, and then just multiply the whole thing by x. Because x itself is a polynomial, so we could multiply that by the created polynomial of the series. Doesn't quite work that way for this one. Notice here it says find the first 3 non-zero terms in the Maclaurin series for e to the x sine of x. The reason for that is because we can create the Taylor polynomial for sine of x. Okay, we've done that already. So that was the sum. This n goes from 0 to infinity, -1, x to the 2n plus 1 over 2n plus 1 factorial. And we can write out the first so many terms of this. We'll do that in a second. We can create a Taylor polynomial for e to the x, which was, oops, I forgot my n up there, which was x to the n over n factorial. And again, these are just supposed to be ones that you kind of already know. And we'll write out the first so many terms. The problem is you can't just multiply those two series together. That doesn't work. You can't multiply a series times a series in that form. So we're going to take the first so many terms and we're going to multiply those out, and we're just basically going to like do a like a polynomial multiplication and combine like terms until we get the first 3 terms set. So if we start writing out the terms, the first term for sine, and these are going to be all the non-zero terms. We don't want to include the 0 terms in here. So the first one is going to be x to the first minus 1/6 x cubed plus 1 over 120 x to the 5th minus, and so on. We probably won't need more than that. If we have to, we'll come back and write another term. But the next one would be an x to the 7th, and it would be over a 7 factorial, and so on. E to the x, there are no 0 terms in e to the x, so we're going to end up with 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1 over 24 x to the 4th. That's probably actually too many terms as it is right now, but that's good enough. All right, so there's multiple ways that you could go about doing this. You could set these up vertically. You could set them up horizontally. However you feel is best and however you multiply a polynomial is the easiest. I used to do this vertically, but I think somebody's actually gotten me into the let's try it horizontal method and see if that works easier for people to see. So what you're going to do is you're going to write out your polynomial. So sine of x will be x minus 1/6 x cubed plus 1 over 120 x to the 5th, and so on. And then you're going to multiply that by the polynomial 1 plus x plus 1/2 x squared plus 1/6 x cubed. I don't think we need that last one. Maybe we do, but I don't think so. All right, so the idea is I want the first 3 non-zero terms, which means obviously there can't be any zeros. We won't get any zeros out of this. But basically is if we start like basically distributing the first term times the first term here, that's going to be x. The first term over here times the second term over here is going to be x squared. The first term times the third term over here is going to be 1/2 x cubed, and so on. Well, I can't have any terms that are in between x squared and x cubed or anything, so looks to me like our highest power term of the first 3 terms is going to be an x cubed. So I really only need to multiply things enough to get me to x cubed. So if I were to take and multiply, now this next one, this will be -1/6 x cubed times 1. So I have minus 1/6 x cubed. If I were to take and multiply that one by the next term out here, that's going to give me an x to the fourth. That's already bigger than what I need. I don't need anything past x to the third in this case, because I've already got an x to the first, second, and third. I don't have any just constant terms, so we don't have to worry about that. If I take this x to the fifth out here and start multiplying up by any of these things, they're already bigger than x to the third. So I think we have enough here to write our first three terms of Taylor polynomials. The only thing we need to do is combine those x cubed terms. So we should get x plus x squared. And let's see, we're going to have a half of an x cubed minus a sixth of an x cubed. If you put everything in terms of sixths, that's going to be 3/6 x cubed minus 1/6 x cubed, which will be 2/6, which reduces to a third. So that should be plus 1/3 x cubed. And yeah, obviously I did a lot of that mentally, but you could write it out if you need to, just to make sure that your numbers come out right. So that would be the first three non-zero terms for the Maclaurin series of e to the x sine of x. Obviously, we could have asked for more terms than that. We could have asked for 4 or 5 or whatever it takes. So you just have to figure out what terms you're going to have to combine after doing your multiplications to make sure you've got those first so many terms. Okay, it's not necessarily going to match the power here, although in this case it did. If we had had a constant term, it may have been like 2 plus x squared. That could have been the first three. The powers wouldn't have matched. Just make sure that you are aware of that. Okay, number 13. Find the first three non-zero terms in the Maclaurin series for tangent of x. Once again, you could try to develop this by taking derivatives. So the derivative of tangent of x is secant squared. When you take the derivative of that, it's going to be a bit of a chain rule. When you start taking the derivative of those, you're going to have product rules and all kinds of messy stuff. So it's going to be very difficult to do. Or, because it says find the first three non-zero terms, we could think of tangent of x as sine of x over cosine of x. So let's write out sine of x. Okay, again, we just did this one at the top. So that'll be x to the 2n plus 1 over 2n plus 1 factorial. And we'll write out the first so many terms there. Cosine of x is the derivative. It's also the even one, so if that helps to memorize it, that's x to the 2n over 2n factorial. And we'll write out the first so many terms there. So let's see, we've already done the sine of x one at the top. That was x minus 1/6 x to the third, plus 1 over 120 x to the fifth, and so on. Let's write out the first few terms of cosine. Of course, we can always extend these terms if we need to. So cosine is going to start with 1, because if you plug in 0, you just get 1 out of all that. And it's all the even terms, so it'll be minus 1/2 x squared. That's what you get if you plug in 1. If you plug in 2, you're going to get plus 1 over 24 x to the fourth, and so on. All right, so the big thing is here, we now have two polynomials. We are dividing sine by cosine. We are dividing polynomials, which means polynomial long division, our favorite. So we are going to put cosine of x on the outside, sine of x on the inside. So it'll be x minus 1/6 x cubed plus 1 over 120 x to the fifth, and so on. Again, we'll add terms if we need to get to the first three, but we should only need those three. We'll see. Maybe we need more. On the outside, 1 minus 1/2 x squared plus 1 over 24 x to the fourth. If I need to add terms, I'm going to have to squeeze those in there, but I'm pretty sure this will work out. All right, so remember the idea is ask yourself, what do you multiply times that 1 to get that x? And the answer, of course, is x. So that'll go on top of the x term. Distribute, so we're going to get x minus 1/2 x cubed plus 1 over 24x to the fifth. And we need to subtract. X minus x is gone. So negative 1/6 plus 1/2 So negative 1/6 plus 3/6 is 2/6, or 1/3 x cubed. 1 over 120 minus 1 over 24. 24 goes into 125 times, so that's going to be 1 minus 5 over 120, which is negative 4 over 120, which reduces to negative 1 over 30. And yes, I am doing that mentally. If you can do that, wonderful. If not, take your time, write it down on the side. It's perfectly fine. Remember that you may not have a calculator for these things, so practice it now. All right. Normally, we would bring down the next term. I don't think we're going to need it because we're going to get 3 terms out of this. So what do I multiply times 1 to get that 1/3 x cubed? And of course, the answer to that is 1/3 x cubed. So we plus 1/3 x cubed. Notice how it lines up directly over the x cubed term. Distribute, so it's going to be 1/3 x cubed minus 1/6 x to the 5th. I don't even need to worry about the last term because it's not going to be important. And we'll subtract. The 1/3 x cubes go away. So now we get, let's see, negative 1 over 30 plus 1/6. In terms of 30 is plus 5/6. So negative 1 plus 5 is 4. So that should be 4 over 30. 4 over 30 reduces to 2 over 15. So it should be 2 over 15 x to the 5th. Again, you'd bring down more terms, but we don't need it. So just ask yourself, what do you multiply times 1 to get 2 over 15 x to the 5th? And that, of course, is going to be 2 over 15 x to the 5th. Okay, I don't really need to do any more of the work because that's going to cancel the 2 over 15 x to the 5th out. We now have the first 3 terms for tangent of x. The first 3 non-zero terms for tangent of x are going to be x plus 1/3 x cubed plus 2/15 x to the 5th. Probably the most difficult ones is the long division ones here to do. They just take the most time. But you're kind of going term by term to do it. So, all right, a couple more examples to go. Last 2 are a little bit shorter, so this should finish up pretty quickly here. Let's evaluate the indefinite integral as an infinite series. So I don't know if you remember, but a long time ago we did something where I was like, okay, we've got cosine of x cubed, even without the x out there. And I said, the only way to do this integral without a calculator is to create a series. And that's exactly what we have to do here. Even with that x out on the front, if we tried u substitution, you'd end up with a 3x squared, which would not get rid of all of the x stuff out in the front. As a matter of fact, it would introduce another x someplace out in the front. So the only way to do this integral by hand is to create an infinite series. So what we will do to integrate this is we'll start off by building the series. We're going to start off with the fact that we know what cosine of x is as a series. Okay, that is the series. N goes from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. There, 2n factorial. Okay, but we want cosine of x cubed. So let's go ahead and substitute in for x, x cubed. So now our series is going to be x cubed to the 2n over 2n factorial. Simplify that because we still need to manipulate this a little bit more. If you don't simplify as you go, you are quite liable to end up with the wrong answer at the end. So this will be x to the 6n over 2n factorial. And then the last thing we need to do is we need to multiply by x. Now again, this one's easier because x itself is a polynomial. So we can just multiply this series polynomial by another polynomial, which means just multiply that numerator by x. So that'll become x to the 6n plus 1 over 2n factorial. Okay, that's a representation for x cosine of x cubed. If I want to find the integral of it, well, integrate. We'll integrate both sides. Integrating that sum is going to get us Don't forget the c, because you're going to have a c out there. C plus the integral, excuse me, the sum, n goes from 0 to infinity, negative 1 to the n. Raise the exponent by 1, so it'll be x to the 6n plus 2, dividing by the new exponent, 6n plus 2, and don't forget you still have a 2n factorial. That is the integral of x cosine of x cubed. And this can actually be used to approximate values. So we could actually do definite integrals on this if we know some specific values. We'll do that in our last section. Okay, one more. If f is a function such that its derivative, f prime of x, is sine of x squared, find the coefficient of x to the 7th in the Taylor series for f of x about x equals 0. Okay, so again, it's going to be a Maclaurin series. But notice it's saying find the coefficient of the x to the 7th term in the Taylor series for f of x, not for f prime. They gave us f prime, but we can start with that. So again, we'll start with the fact that we know what sine of x is. Okay, sine of x is this sum, which we have used several times now. So hopefully you're getting used to it. I want to get sine of x squared. So we will substitute x squared in for x. And I apologize if I'm going a little bit quicker. I know how to write these sums and everything pretty fast usually. So, all right, let's substitute x squared in for x. So that'll be x squared to the 2n plus 1 power over 2n plus 1 factorial. And we'll simplify. So let's see. X squared to the 2n plus 1 becomes x to the, multiplying the exponents, 4n plus 2 power over 2n plus 1 factorial. But that's an expression for f prime. If I want to get back to f, we're going to have to take an antiderivative. So f of x is going to be the antiderivative of what we just found. And the antiderivative of what we just found is going to be some kind of a c plus the integral, I keep saying integral, the sum from n equals 0 to infinity, negative 1 to the n, raise the power by 1, so x to the 4n plus 3 divided by 4n plus 3 times 2n plus 1 factorial. We want to know, now that we have f of x, the coefficient of the x to the 7th term. So what would you have to plug into n to give me x to the 7th? Hopefully the answer to that's pretty obvious. The answer should be 1. So we're going to plug in n equals 1, and we'll find our c sub 7 coefficient. If n is 1, it's going to be a negative. If n is 1, we're going to have x to the 7th. If n is 1 in the denominator, we're going to have, let's see, 4 times 1 plus 3 is 7, times, plugging in a 1 to the factorial part gives me 3 factorial, which is 6. So ultimately what we get here is negative 1 over 42 x to the 7th, which means that c sub 7 is negative 1 over 42. And that's the answer that they were looking for. All right, I realize this was a very long section. It usually is. If we didn't get a chance to finish this in class, finish it up for homework. The nice thing about this particular section is that this is really the penultimate of everything. So we will finish the entire unit up with 11.11, but this is really like, this is starting to wrap everything up for us. If you didn't catch everything and I went a little too fast, go back and rewatch the parts that you need to, slow things down so that you can understand. All right, otherwise that should be it for this section.